So we have another remote presentation, the last remote presentation for this session. It will be by Liang Wang from Bristol about Raven. So he's not available online, so we'll be playing the recorded version of the presentation, and there won't be any Q&A after this for this presentation.
Hi everyone, my name is Liang Wang, and I'm an associate research scholar from Princeton University. Today I will introduce Raven, a network privacy solution designed for enterprise networks. This is a joint work with June, Petit, and Jane. Nowadays, enterprise networks face increasing threats against the privacy of their clients. Unpaid eavesdroppers may try to learn sensitive information about an enterprise network and its client, such as the client location and activity. Many attacks are feasible because the attacker can see the real client IP. In the world of IPv6, the situation gets worse because the IPv6 addresses are usually persistent, making some attacks easy. For example, the IPv6 address assigned to a client usually consisting of two parts, network prefix and the interface ID, or IID. When the client moves between different networks, the prefix changes, but the ID may remain unchanged, which enables location tracking. And unpassed attackers can build profiles based on traffic associated with a given client IP to track user activity, or perform more advanced traffic analysis attacks, such as website fingerprinting, to infer the website the client is visiting. In the website fingerprinting case, the attacker doesn't even need to know the true client IP. So there are many solutions designed to protect privacy, but they are mostly client-based solutions like Tor and require individuals to set up some software. So we ask this question: how can an enterprise network protect the privacy of their clients? Obfuscating or hiding client IPs do mitigate IP address-based attacks, such as location tracking, because the attacker cannot identify a client based on the patterns in the IP address. For attacks that leverage multiple connections from the same IP, we want to make sure different connections have different IPs, but still there are some attacks that only look at a single connection. For those single connection-based attacks, a possible solution is to change the client IP in the middle of a connection multiple times, or change IP per subconnection. Here we introduce a new privacy property called subflow or subconnection unlinkability. With subflow unlinkability, a connection should look like in multiple independent connections to the attacker. The client IP changes frequently, so it becomes meaningless to the attacker. Why it can defeat single connection-based traffic analysis? Say a successful traffic analysis attack needs at least 100 packets from a flow. If we rotate the client IP every 20 packets, the attacker may see connections of 20 packets and cannot launch efficient attack. There are two challenges: how to frequently change IPs without disrupting ongoing connections, and how to manage IP assignment and rotation efficiently. The enhancing privacy usually comes at the cost of performance. For example, our subscription net can already provide per flow IP using a mapping table, but it's hard to scale it to IPv6 networks and handle asymmetric routing. Seems that it is inevitable that we need to sacrifice performance if we want to address the two challenges correctly to provide stronger privacy. Fortunately, we have Quick and IPv6. Using them, we design Raven, a network solution that protects the privacy of all clients in the network. Raven leverages quick connection migration to change IPs without disrupting connection, A programmable switch runs at the border of a network to encrypt and decrypt IPv6 address and at line rate without maintaining any state. Raven is a network layer defense that is complementary to defenses at the up layers. Later we will show Raven achieves a good privacy and performance trade-off. We address the first challenge using Quick. Quick was developed by Google and recently becomes the standard. Quick is the foundation of HTTP3. It becomes more and more popular with the support from major tech companies such as Google and Facebook. Quick provides a set of new security, performance, and privacy features. One of the key features is called connection migration, which allows the client to change its IPs in the middle of a connection without disrupting ongoing connections. PureWork has already used this feature to design privacy-enhancing systems. Now let me explain how we achieve stateless encryption. Here is an example. Let's assume we have a /64 network. We design a special address scheme. The first 64 bits is a constant network prefix, and the last 32 bits is the client ID, and the rest are just zero or random. Our goal is to obfuscate the client ID and the client port. To do this, we use a lightweight line-read encryption on programmable switch to encrypt client ID port and some random padding. We store the ciphertext in the client IPv6 address and port as the new IP address and port. 64-bit encryption is not as secure as AES, so we use high-speed key rotation to increase security. Each time key changes, the client IP also changes. The control bits are used to facilitate key rotation. Now with quick IPv6 address encryption and encoding and key rotation, Raven achieves subflow and linkability and is able to provide protection against the first two types of attacks. Unfortunately, this is still insufficient for mitigating those advanced traffic analysis attacks, because there are other identifiers in the packet headers, such as the quick connection ID, IPv6 flow label, and the extension headers. When the attacker looks at the encrypted IP and port, the packet appears to be from different connections. But if all these packets share the same connection ID or CID, it is trivial to figure out they belong to the same connection. Therefore, we must change the CID and IP port at the same time. We only need to care about the connection ID here because we found that the issues caused by other identifiers are easy to address. But the CIDs need to be negotiated before usage. So CID negotiation is protected by Quick. The switch doesn't know the negotiated IDs in advance, so it cannot set arbitrary connection IDs. Our solution is called division of labor. We let the client actively rotate connection IDs and control when and how often, while the network switch will encrypt IPs based on the public connection IDs. Recall that in the encryption, we need to add some paddings. In Raven, the paddings will be generated based on connection IDs. Now, every time the connection ID changes, the client IP and the port will also change. Active connection ID rotation is not supported in the current Quick, so we create a modified version of Quick called Quick Star, in which the client can control the connection ID rotation. More importantly, we remove context control reset and path validation for Raven-related migration. This greatly improves performance. Note that we only change the Quick protocol and no need to change the client or server-side software. And the Quick Start is not required if the network only wants to achieve per connection ID and low-frequency IP rotation. So we deploy Raven in a /64 test network and evaluate its security. We collect Raven traffic by repeatedly visiting GitHub pages through a Quick proxy. We use the Quick proxy because GitHub doesn't support Quick. Here is an example of real-world Raven traffic. If we look at the traffic, the client has used three different IPs in one connection. The attacker only knows the connection are from the same network. We further evaluated web page fingerprinting attacks against Raven. In web page fingerprinting, the client is visiting resources posted on the same server IP port, and the attacker tries to figure out which one. This requirement is important because Raven only changes client IP, not the server IP. It might be trivial to link sub-connections to connections based on different server IPs. We examined the quick traffic from our campus network and found even under current limited quick deployment, this case is very common, so our scenario is realistic. So more details can be found in our paper. We perform a comprehensive performance and security evaluation. We assume a strong and adaptive attacker that can see all the traffic. This is different from pure work on traffic splitting, where the attacker can only see the traffic on a single path. So we consider multiple settings and different combination of parameters. And in short, we found that the Raven can effectively mitigate the state-of-the-art web page fingerprinting attacks with relatively low performance overhead. So we want to mention that Raven can be used to protect DNS and NTP traffic. Here, in this case, we do not need any modification to the DNS and NTP protocols, and we do not need collaboration from the server. Raven can randomize the client IP in each outgoing DNS or NTP packet to prevent malicious public servers from tracking client. Raven can also work with other protocols with good mobility support, such as WireGuard. We have an example in the paper. So for future work, we want to extend the use cases of Raven. For example, deploy Raven at on-path networks or ISPs instead of client-side networks. We also want to use Raven to obfuscate the server IP addresses. And we are considering use more advanced programmable hardware so we can implement the standard encryption schemes such as SPEC and Simon or AES. If you have any questions, please send your question to my email, and you can look at GitHub for the code and the dataset. Thank you.